In this video, we'll take a little bit of time to go look at some of the problems from the quiz on sections 2.6 and 2.7. So on the front page here, we just wanted to find three derivatives: the derivative of this function, the derivative of this function, and then also the derivative of this function. If you're going to take the derivative of the function given in number 1, you have to recognize that you have one function of x right here, e to the 3x, another function of x right here, sine of 4x, and that you're going to have to use the product rule. So we are going to have to use the product rule for this, and the product rule says take the derivative of the first function of x. So in this set of parentheses, I need the derivative of e to the 3x. Now I don't have a derivative formula for e to the 3x, but I do have this derivative formula, the derivative with respect to x of e to the x. That's equal to e to the x. That's a formula that we looked at last week and we've been using off and on ever since. So I can't apply this formula directly in order to take this derivative, but what I can say is I can say 3x is an inner function, and I can use this derivative formula and say that the derivative of my outer function, using the chain rule, would be e to the normally x, but I'm using this with the chain rule, so I'm going to put the inner function right there. So my inner function would be 3x, and then I'm going to finish the chain rule by multiplying by the derivative of the inner function, which would just be multiplying by 3. So there's the derivative of the first function of x, but keep in mind we initially said we were going to use the product rule because we have this second function of x multiplying the first one. So the product rule is going to continue with the original second function, sine of 4x, and then we're going to add to that the original first function, so e to the 3x, and then we're going to multiply this by the derivative of the second function. And similar to what we said back here a minute ago, we don't have a derivative formula for sine of 4x, but what we do have is a derivative formula for sine of x. The derivative of sine of x is cosine of x. I'm not going to put cosine of x right here. I'm going to put cosine of the inner function, so cosine of 4x. And I'm going to have to finish the chain rule by multiplying by the derivative of the inner function, just multiplying by a 4. And yeah, you can clean this up a little bit if you wanted to simplify it, but that would be a valid form of the derivative. So there's your derivative in number 1. Moving on to number 2. Little different notation. This operator notation just means to take the derivative of whatever's in the set of grouping symbols immediately following it. So the derivative of natural log of cosine of x to the 4th is just going to require us to use the chain rule very carefully. I have this outer function, natural log, and the derivative of natural log from a formula that we looked at last week is that the derivative of natural log of x is 1 over x. I can't use this formula directly because I don't have an x within the natural log. I have this big inner function. So I'm going to have to use the chain rule in conjunction with this. This derivative is going to end up being equal to 1 over, not x, but the inner function, cosine of x to the 4th. And then I'm going to finish the chain rule by multiplying by the derivative of cosine of x to the 4th. So the derivative of cosine would be negative sine. I'm not going to put an x there, I need to leave the inner function there. And then, since I had more than an x inside this trig function here, I'm going to have to finish another chain rule by multiplying by the derivative of the innermost function. And the innermost function is x to the 4th, so the derivative of x to the 4th would be 4x cubed. And that would be your derivative in number 2. Moving on to number 3, and number 3 is the toughest one on the front page, and this was a pretty big issue for certain people on the quiz. We looked at logarithmic differentiation quite a bit when we were discussing this section together, because it's probably the toughest idea to get a decent feel for from this section, but you don't need it very frequently. The only time you need logarithmic differentiation is in a situation where you have an x in the base and an x in the exponent. Here we have an x raised to the tangent of x. Since we have an x in the base and an x in the exponent, what we're going to have to do is we're going to have to use that logarithmic differentiation process. And the reason why we're using it is so that we can get this exponent out of the way. Because if we introduce a natural log to each side of this equation, we can then use a property of logs, the down in front property. That exponent can come down in front as the coefficient of the natural log. And now we no longer have a situation where there's an x in the base and an x in the exponent. What we are going to have to do here is we're going to have to develop a derivative, dy dx, and since this isn't solved for y, we're going to have to be a little bit careful when we do this. We're going to take the derivative of this side with respect to x, and we're going to take the derivative of this side with respect to x. So I kind of ran out of room to write that, but I'm doing the derivative of both sides with respect to x. I'm going to do the derivative on the right side of the equation first. I have a function of x times a function of x. So I'm going to have to use the product rule. Product rule says derivative of the first function of x, derivative of tangent of x, is secant squared of x, times the original second function of x. So there's derivative of the first, original second, plus original first, which would be tangent of x, and then the derivative of natural log of x would just be 1 over x. So there's the derivative on the right hand side. Derivative on the left hand side. A little trickier because we need to assume that y is a function of x, and we actually know that y is a function of x in this case, but y is a function of x, and so we have an outer function, natural log, and an inner function y. Taking the derivative of that using the chain rule is going to be 1 over the inner function. So just like we did in number 2, the derivative of natural log is normally 1 over x. We're not going to put 1 over x, we're going to put 1 over the inner function. And then we need to finish the chain rule by multiplying by the derivative of the inner function, which would be dy dx. The only difference between this and the first two is we don't have f prime solved for, we don't have the dy dx solved for, the derivative's not solved for, it's 1 over y times dy dx. So to isolate the dy dx, we would just have to, get rid of this piece by multiplying each side by y. Dy dx would then end up being equal to exactly what we have here. So I'm just going to copy all that down again. Since I'm writing out an extra line, I'm going to take a minute to just kind of simplify this. If I do top times top, bottom times bottom, I'm looking at tangent of x over x. And then I'm going to multiply each side by y. Now I could put a y right here, but my original function was solved for y, didn't have any y's on the other side. So what I'm going to do is rather than putting y here, I'm going to put what I know y to be equal to, x to the tangent of x. So that would be your 3 derivatives on the front of this quiz. We'll take a look at problems 4 and 5 from the back in the next video.